Pursuing PhD under the guidance of Professor Dr. P.L. Chithra at University of Madras. Our work proposes spatial-aware hierarchical graph network for volumetric medical image segmentation, that is SAGNN. This architecture is proposed to overcome the challenges faced in the transformer model. As transformer model imposes a uniform grid structure across all the pixels. It leads to a relational imbalance between the pixels. To overcome these issues, data is considered as a relational graph. This is done by integrating the GNN at the bottleneck of the swing transformer architecture. The bottleneck, though it is low in resolution but high in a feature dimensionality. By introducing GNN, it also reduces a false positive across the earlier layers, and it consists of channel attention with a six block, that is squeeze and excitation blocks, to retain the necessary channel information, and it is concatenated with the spatial attention with a Sobel filter to retain the edge information. The novelty of this method lies in a swing graph hybridization, the anisotropic edge weights, and learned spatial embedding and dynamic spatial positional bias. This learned spatial embedding and dynamic positional bias adjust dynamically according to the relation between the token pair and they feature interaction between the pixels. The overall architecture of this LSPB and DSPB is shown in the figure 6. The input is divided into non-overlapping patches, then flattened, split into very key values, scaled, reshaped. Then it is concatenated with the key values. After that, the DSP and LSC is reshaped, then concatenated with key and query values. And check for mask. If there is a mask, the reshaped softmax is applied and normalized. Then, if there is no mask, the softmax applied and then normalized weight aggregation is performed, reshape transport and flattened. The graph hybridization is performed by calculating the Euclidean distance between the two nodes, where alpha is the learnable weight and it is a direction dependent. This is shown in the algorithm 1. The initialization of the nodes, then aggregation weight calculated between the nodes, and the updation of each node, and the output of the bottleneck. This is shown in a figure 7, where this three are the tumor regions, the tumor core, edema, and enhancing tumor. Then learned spatial embedding is applied, and dynamic spatial proportional, which is a direction dependent, and the anisotropic graph node is calculated between each node based on the node weight. It's shown based on the node weight. It is divided into strong edge, medium edge, and weak edge. Based on this, it is classified. Each classes are classified. Based on this, each classes are classified. It's shown in the figure 7, and the final segmentation of SAGN result with the ground truth is displayed in this figure. These two images shows difference between the normal transformer, and after applying learned spatial and dynamic position, the figure in the right shows abruptly the classes and the tumor regions strictly. On the tables, compilation is steady by adding and removing the each components of the SAGN, which gives an improvement of 3.5% in dissimilarity coefficient, and also gives 80% decrease in the false positive of tumor boundaries. This is showed in a table 1 and 2, and it is also compared with the baseline models NN unit along with the other model. Its components analysis has been made quantitatively and qualitative. The quantitative method is shown in a table 4 and 5, where qualitative method is shown in the figure 7. Each component has been analyzed, its spatial consistency and data set for across 2020 to 2024 has been validated using SAGN net, and outcome of this model, it outperforms all other models by increasing a 5% in its dice score and 18% reduction in HT95 over NN unit. Thank you.